Good afternoon. Our Capstone project is called SmartEco Kettle, and it's an energy efficient and intuitive redesign of the traditional electric tea kettle. So we're going to introduce ourselves. My name is Marvel Pilati. I'm an electrical engineering student and also the team leader.
My name is Charles Barnes. I'm computer engineering. I'm software and machine learning lead.
My name's Alec Perron. I'm an electrical engineer. I'm part of the hardware and biometrics research.
So this is just an outline of all the things that we're going to cover in this presentation. So our project motivation. One of the main reasons we decided to go with this project is because we believe it's going to be a strong market. Kettle ownership rates have been rising internationally in Europe, in Asia and Africa, and even in the US, where it hasn't been a popular product. For example, in Libya, about 42% of households owned a kettle in 2013, where 5 years ago, in 2008, it was only about 8%. In the UK, which is probably the biggest market for tea kettles, electric tea kettles in the world, about 97% of households own a kettle, and about 40% say they use it multiple times daily. And by 2030, 40% of the cooking electricity consumption in the UK will be from electric tea kettles. And because of that, there hasn't been a lot of change over the couple of years in terms of advancing electric tea kettle technology. It's been kind of stale, but that doesn't mean there aren't problems to solve. For example, demand spikes. Electric tea kettles are one of the most high power requirement appliances that you can find in a household. When you turn them on, you usually find that there's a spike in power drawn, and that differentiates between the low and medium demand profiles of the households. And compounding this problem is the time of operation. Usually people who have tea kettles use it during the same times each day. So in the morning when they get up, or during lunchtime, or when they get home from work. So this kind of compounds, and it's so well known in Britain that it has its own term. It's called the TV pickup effect. That's when there's breaks in programming in popular TV shows or in big games. You'll see that there's a huge spike in demand that the national grid has to deal with. So that's one problem. Another thing is overfilling and reboiling. And this isn't a problem inherent to the device itself, it's just with how people use it. When people make tea, they don't usually fill out how much they need exactly. They usually just eyeball it. So because of that, you can see here, about 75% of households admit to overfill, which wastes about 68 million pounds annually. And reboiling as well. Sometimes when people make it, they forget, they come back, and they have to reheat it again. So that's another problem that wastes energy. So to solve these problems, or to at least address them, this is our proposed design. We want to incorporate an induction heating element to increase the efficiency of the electric tea kettle. We want to attach a water tank with the flow, with the valve to control the flow. We want to seal the kettle to prevent any kind of heat loss. And we also want to add a microcontroller with a valve to control the valve and the heating element. And the kettle will be, the power electronics in the kettle will be controlled by a Bluetooth module, which will receive and send instructions to and from a mobile app. And separately, there will be a database to collect and analyze usage data. So this is just a big picture of our proposed design. And you can see it's kind of split into 3 parts. But the main idea is this. We want to remove the kettle, the idea of a kettle being an appliance in the kitchen, and instead put it into someone's pocket. Almost everyone nowadays has a smartphone, and we think it's really powerful to have an app that can control all the functionality of a tea kettle, so that people can control the tea kettle and without ever getting up off the couch or off the table, they can control it remotely. So for example, the mobile app can send instructions on when to start and stop the device, how many cups of water to heat up, and what temperature to keep the water at. And here you can see on the left-hand side, you can see some of the electronics that we'll be incorporating into the kettle. For example, there's going to be the microcontroller, which will, for now, be an Arduino Uno. There'll be a Bluetooth module, again, to send and receive instructions from a mobile app. We'll have the induction heating element and an iron temperature sensor. And then we'll also have a control valve, which will control the amount of water. Then we have a separate idea in which there will be a database which stores all user data, and we also want to integrate it into the Internet of Things, so that, like I explained earlier, a problem was these big spikes during commercial breaks, or commercial breaks during big games or popular programs. We think that maybe using an IoT application integrating the Internet of Things, we'll be able to send information to the mobile app that tells people, hey, there's going to be a break in this program. Would you like us to maintain for this time? So this is our table of alternative approaches. On the top is you see the criteria: cost, power consumption, range, and speed. And those are the values we picked. On the bottom, you can see the values, the normalized values, and on the right, you see the total weights, with the most weight going to power consumption, and then going to range, and then cost, and then speed. We use this table to decide between Bluetooth or Wi-Fi implementation for our device, and because we wanted the power consumption to be low, and most of the power going right into heating the water, we decided to go with Bluetooth over Wi-Fi. So this is our engineering marketing trade-off matrix. On the left side, you can see some of our marketing requirements. One thing is obviously we want this device to be eco-friendly. I think that's going to be a huge selling point for our device. Another thing we want to market is our smartphone integration, to show people that all the functionality can be accessed through a mobile app. We want this device to be attractive. About 80% of people who actually shop for electric kettles don't base their decision based off the features of the device itself. They just base it off the looks. So we don't want it to be an eyesore. We want it to fit into a kitchen environment, and we want it to look good. We also want it to be intelligent and marketed that way. We want to show that this can automate a lot of the process, so that people in the morning when they're in a rush, they don't have to manually make tea, or when they come home from work and they're tired, it'll have it made for them. So I think that's going to be another big selling point for this device. And obviously we want to keep the cost low. Then we have our engineering requirements. We want this to be as efficient as possible. The electric tea kettle is already one of the most efficient ways that people have to heat up water. It trumps the microwave or the stovetop in terms of heating water. But using the induction heating circuit, we believe, will increase the efficiency from about 80% to 90%. Then we want also our device to have high power ratings. We want this to be able to be plugged into a wall outlet, and we want all the electronics to be operating at high voltages. And because the electrons will have to switch pretty quickly in our circuits, we want those electronics to be highly rated. We also want to keep the cost of our material low, and we also want to keep the setup time as low as possible, so that people don't have difficulty setting up the app or the device. Okay, here are some market solutions that already exist that we thought were pretty interesting and that we took some inspiration from. One of them is the Teflo tea kettle that you see. It's kind of a standard tea kettle, except that it has wireless capability, so you can control a lot of the functions of the tea kettle wirelessly. And it also has a heart rate sensor, which claims that it could, based on your heart rate, make the perfect cup of tea for you. So that's some of the claims. And some of the cons here are that it doesn't fix the overfilling issue, and it's also pretty expensive. I think it retails at about $400, so it's aimed at the premium market. Another one is the Mito, and this is a little bit more interesting because it solves the overfilling issue in a really interesting way. What it is an induction heating element right here, and it has a metal rod, conductive rod with a flat base. So you can put whatever amount of water that you're heating up exactly it'll heat up that much exactly. It doesn't matter what kind of surface it is, what kind of receptacle you're using. It's very efficient and it's very straightforward and easy to use. But one of the cons is that its heating times may vary based on what kind of receptacle you're using. For example, if you're using a thick bottom mud, it might take a little bit longer. It also doesn't hold heat for that long because it's open to the environment, so a lot of heat gets lost.
So this is the physical diagram that we proposed for our project. We have the user, the control, and a cloud server. The user will interact with the application. The application goes to the control, which will use artificial intelligence through machine learning to interact with our cloud server. Our cloud server is going to act like a virtual relay that will send a notification to the user, either if they want to control the temperature, make it warmer, cooler, or maintain that temperature. So this is a tree diagram of our smart tea kettle. It's composed of 4 components right now: a controller, phone, cloud server, and application and display. So the controller corrects our signal, processes data, and sends it to the phone. And the phone serves as storage for information and also as a relay to our cloud server. Our cloud server is going to analyze the information from the phone and relay it to the application or display. And the application or display serves as an output for the cloud server analysis through a notification. So for our related theory, we're using some terms from electromagnetic theory. So we're using a derivation of the Biot-Savart law for our magnetic field derivation. When simplified, it becomes mu0 I over 4 pi r squared, line integral of dl. So that's the differentiation of the length of the coil. And that simplifies to mu0 times the current over 2 times the radius. So also we want to use this circuit. It's going to convert a DC input into AC, which we feel works best for our work coil. It uses soft switching through these transistors, and then it's filtered through a CLC filter to the work coil.
We didn't show the gate drive circuitry here, but it'll be controlled by the Arduino. The Arduino has its pulse width modulation pins, and we'll be using that to switch on and off those transistors.
So this is a data flow diagram. It shows the user interface interacting with the microcontroller, database, cloud server, and application and display. It also shows what the role is of each operation. So the microcontroller serves as data correction, which filters the signal to the database, and then the database simplifies the data for the cloud server, which then sends that simplified data to the application or display to be shown as a notification to our user. So this is also the use case diagram that we have. For our models, we have the user, the control, and the database. We propose using a heart rate sensor similar to the Teplo, but that's not part of our 40% right now. That's probably going to be worked on during winter or the spring semester. So right now, the user would interact with the heart rate sensor. The output from the heart rate sensor would be sent to a control, which would then be sent to the artificial intelligence. Artificial intelligence would send that data to be stored in a database, and the database would send that to the cloud server through machine learning or AI, and that would send notifications back to the user based on like their heart rate or other information. And this is also basically a simplification of the use case diagram through an activity diagram. So the user is going to initiate brewing, and that's going to split off into the control and the database. So the control is going to read our sensor outputs, deliver control inputs to our artificial intelligence, and feed the AI output to a database. Then the role of the database is to store the AI output and send the output to the cloud server. Once that's completed, then the user will receive a notification, or the kettle itself will regulate the water temperature. So this is our functional decomposition for our tea kettle. It's going to be powered by 120 volts AC, and it's also going to have inputs of temperature and water volume. The only output is going to be the display notification. So given our inputs and outputs, the microcontroller is going to control the data that was input and return notification to the user to initiate the tea brew. So for our level 1, we have our induction coil and our microcontroller. For the induction coil, obviously the input is current and the output is heat. So we basically want to use an induction coil as the form of primary and secondary to heat our tea cup. And the microcontroller is going to get a voltage and current signal. It's going to correct the signal and serve as a control for easy processing. And then, as we discussed earlier, our wireless connectivity is Bluetooth over Wi-Fi. So we're proposing to use a binary input, either logic level 0 or 1 to send a high or low to our microcontroller. This will power like the switches for the valve for our water volume control. It'll also control the temperature if we need to, either to maintain the temperature or make the tea warmer. And Mr. Pilati here is going to show our demonstration videos.
So what you're looking at right now is the app that we have. It shows the start and stop buttons. It also shows the status, which you can't see clearly, but what you see here are the Bluetooth devices that we could connect to, and that he just selected was our device for the valve. And when you hit start, you can see that the water starts flowing, and when you hit stop, it should automatically stop. So that shows that the valve works. So this demonstration is for the infrared temperature sensor. What you're seeing on the screen there are the temperatures of the object that the sensor is measuring. Right now it's not pointing at anything. If I put my hand over it, the temperature should start increasing. And you can see there that it goes up a little bit to like 90 degrees Fahrenheit. And then this water is cold, so the temperature should drop down. And you can see there it goes down to 60, 66. So that's the video of the temperature sensor working.
Here we have our iteration table. We did a series of tests over the course of the semester, just generating. We have most of the spin specifics. We have the testing of our Arduino Uno, the Bluetooth HM10 module to connect that. Then we have our valve, which we tested. As you can see in the previous video, it worked. We had, for at least for the Arduino, there's a couple iterations required just because the different configurations we needed to do in order to get it to work. Same with the Bluetooth, we were actually considering getting a totally different module just because connectivity issues. The valve was pretty functional. Just had the circuit right with a solid-state relay. And the mobile app was difficult just because I tried to get it working on Android Studio, and we had a difficulty, but we eventually got it working with an MIT app better. And then we have our temperature sensor, which just implied hooking it into the circuit, and finally an integration test with combining the three of what we have thus far. And here it is breaking down specifically the unit test, which specifically is the testing of each individual module to make sure proper functionality has been achieved. The Arduino, Bluetooth required 2 iterations for a pass, the valve passed first time, the mobile app required 2 iterations, temperature sensor, and there's a bunch of iterations required for the integration test. That gave us a little bit of trouble so far, but we have more to do in the coming semester. This is our current cost estimation. Right, we're starting pretty low. We're about $84.52, which is far short of where we thought we would be actually. Right now we have the wire, the board, the valve itself, the sensor, and then miscellaneous with the duct tape required for the construction of our valve setup. It's going to be, the costs are going to be increasing as we add proper fitting, probably 3D printed, in addition to various costs foreseen in the future. But right now we have a sizable amount of money left in the piggy bank for if we need any rainy day purchases. So thus far, we've gone over, we're developing an electric kettle that will allow societies to easily alleviate their their energy problems, specifically the TV wind-up time. And if you can make it, instead of having a tea kettle that will literally understand when, it'll predict when you want tea, so you won't have to go through the constant reboiling. It makes it much easier of a process and allows you to stay in your routine much easier. Consumer benefits, electrical companies benefit, countries benefit. But right now, at this point, we have preliminary software with the mobile app. Might need different changes as we evolve it more into the cloud server, as well as implementing the machine learning. Most of the hardware is done. The only thing we really need left is to finalize the construction of the induction coil, just because they gave us a little trouble, but after we get to that, it's just a matter of beautification and assembly. And then actually, that's the conclusion. So in the future, going forward, we're going to, over the winter, we'll be looking pretty heavily into implementing machine learning. We're going to lay a framework for the database, Firebase, AWS, and then finalize the circuit, completely construct. In the spring, find a 3D printer for the beautification so it can sell well, so it looks pretty. As we've mentioned before, most of the reasons people buy them is because they look good. And then finally, integrate the machine learning element into it so it can, it delivers as we set out for, which would be the couple codes and standards we needed to hold ourselves to. We were alerted to the idea, we are dealing with potable water here, so something that could be a problem is the valves or the circuitry we use leaks, so this could potentially be harmful. So under California's OEHA Proposition 65, which is a warning basically to certify that this could be dangerous, and so it's a warning. Once we get more close to the end goal, see if we can get as many things up to code as humanly possible. But once we just have a functioning prototype, that's our primary goal. We're using Bluetooth, so we're using IEEE 802.15 WPANS for so following the Bluetooth standards that we're using. So right now we're using a serial database system and a serial system for communication in between the Arduino, various sensors, and computer right now. And then we're dealing with circuitry, so the NIST, electronic compliance requirements, safe circuits, hopefully not building any destructive elements. So we have a couple ethical considerations we'd be dealing with as far as the scope of our project. First and foremost, we're going to be dealing with a lot of user data. Are we in public with that? Is that going to be a part of our business plan? Probably not. We don't really consider that at this point. We'll have to build that, and we'll tackle that next semester. But this is ultimately designed to not really be used that much, but we have to also consider how invasive is this. Prediction is to be questionable. How much does it learn you, and how much can other companies benefit from this data and this knowledge? And then, on a specific note, 7.8 section of the IEEE Code of Ethics, specifically Section 9. No malicious actions. We aren't trying to harm any others in the creation of this project, only benefit the world and ourselves at large. And then, here are a couple of references. Thank you for sitting through our presentation. Really appreciate it.
Any questions? Thanks.